Welcome to my video lecture based on electric circuit theory. Paper code PCE 301. This total syllabus is based on out curriculum, and whatever lecture I am delivering for electric circuit theory, those are based on out syllabus. In this lecture, we will deliver some numerical problems on magnetic coupled circuit. In my previous lecture, I have described about magnetic coupling, what is reluctance, what is circuit EMF, what is mutual EMF, and how the magnetic coupling is coupling, and what is dot convention. When this mutual EMF will be positive, will be negative, those things will be discussed already in my previous lectures. So, myself, Energy, Assistant Professor of Electrical Engineering Department, Dr. Shul, Institute of Technology and Sports Physics. Previously, it was known as Dr. Engineering College, and this institute is JIE school. So, various numerical problems related to magnetically coupled circuit will be described here. Actually, for any kind of circuitry chapters or in modules, it is very important to solve different types of numerical problems. Mainly, numerical problems are very important in this regard. So today I will take some numerical problems from the book of OBJ Chakraborty of circuit theory for your better understanding this chapter of magnetic coupled circuit. So let us consider the first problem. Determine the current I1 and I2 in the circuit shown in the figure using T-equivalent circuit for the linear transformer. Basically, the structure is just similar like a linear transformer. So this type of circuits are known as linear transformer circuits where mutual induction is happening, and we can see that the dots are present that is opposite directions. That means the mutual induced EMF will be in reverse direction and it will be just class as per the T equivalent of the circuit. So using the T equivalent circuit for linear transformer, which we have read in my previous lecture, already I have illustrated that how the T equivalent circuit can form from a linear transformer structure. So from there we can directly use this formula, that is A1 plus M, that is A, that will be 9 MV, and A2 will be A2 plus M, that will be 6 MV, and AC will be minus M, that is minus 1 MV. So now we will change this linear transformer formation to the T equivalent network in this, and we have put the values of LA, LB and LC, and those values we have put it here. This is minus J1. Now inserting the T equivalent circuit in the original circuit, so our actual circuit becomes like this. That means this part previously it was mutual induction part. In circuit plus separate. Now we have converted this circuit to the form, and we have just overlapped this one with the previous circuit. So now the circuit is looking like this one. So we can apply KVL in different loops and we can form the mesh equations. So we apply KVL in the first loop and we are getting that J6, basically 6 angle 90 degrees, it is J6, the lower voltage is J6. Angle 90 indicates that J. So J6 equals to I into 4 plus J9 minus J1 plus I2 minus J1. So in that way we can form the equation 1 and equation 2 also form like this. Here will be I1 into minus J1 plus I2 into n plus J6 minus J1. So that is we have formed the both equations. And using our tool, we have solved the values from these two equations, and we are getting the value of I1 and I2 like this. So these are the two values of I1 and I2. Here we are getting I1 value is 0.67 angle 27.14 degree and I2 is 0.06 angle minus 90 degrees. And both units will be ampere because it's current. Now we are going to the next problem. For the ideal transformer shown in the figure, determine the average power dissipated in the 10 kilo ohm resistor. That means the average power from this resistance you have to calculate. Okay. So here the turn ratio is given 1:10. So using that value, we have to calculate the input impedance. So definitely the input impedance value will be JL divided by N square. And the value of L will be 10 kilo ohm, that is 10 into 10 to the power 3 ohm divided by 10 square, where it is the number of turns. So the input impedance value is 100 ohm. Now we will calculate the current. Current calculation is definitely divided by R. So our total R is 50 divided by 100 is already here, and from here we have calculated this one 100 ohm. So the primary current is 50 divided by 100 plus 100, that is 0.25 ampere. And secondary current, by using transformer formula, that is RP equals to I1 by N1. If this comes from turn ratio for that is I2 by I1 equals to N. So from here we can calculate this secondary current value, that is 0.025 ampere. Now average power dissipated in 10 kilo resistor, that will be using the same power formula, that is I square R. So here I square R, because our 10 kilo resistor current is I2. So we have taken the current I2 square R, and here R value is 10 kilo ohm. So it will be 100 to 10 to the power 3, that means 6.25 watt. So the result we are getting here, that is 6.25 watt. Next problem. Obtain the dotted equivalent circuit for the coupled circuit shown in the figure and use it to find the voltage across the capacitor of minus J10 ohm reactance. So here you can see this is a transformer circuit where in the primary and secondary a capacitor is connected, and in both sides we are getting some voltage, input voltage and output voltage also. So by the dot convention, if we assume that the current is entering in the top left of the coil and place a dot at this terminal, then the flux direction of this current will be upward. Now in this law, the flux at right while marked the upward direction to oppose the first flux. In that case, the current will be winding by the top terminal where another dot is placed. Thus, the dot equivalent circuit will be shown as per the given figure. So this circuit will convert it to the equivalence form in that way. See here, this is the input voltage 10 angle 0, this one. Then 5 ohm resistance is present, so 5 ohm is connected in series with that. Then one J5 inductor is connected, so definitely here one self-induced EMF and mutual induced EMF will be there. So we are taking that the current is coming through this way, so we are taking that the dot is here because the current is entering mode. This inductor is placed in entering mode. Now the capacitor is connected between these two windings, that means it is in the middle part. So this is the capacitor portion, the value is minus J10 ohm. Now this one is connected with another inductor. Definitely it is transformer circuit, so the EMF will be induced as per Lenz's law, it will be just opposite direction. So then dot will be from leaving part. So here we have placed the dot in the leaving portion, this one. And another resistance is connected 5 ohm, this one, and output is given, that is 8 angle 90 degrees. So this is the equivalence form of this circuit. And in between this, it is given that the mutual inductance value M is J2, this one. So here the value of M is J2, that is shown here. Okay. So now let's calculate. So by applying KVL for the two meshes, again we have taken the KVL mesh equations. So this is loop 1 and this one is the loop 2. And we have applied KVL in loop 1 and we are taken at I1 into all graph present 5 plus J5 minus J10 minus I2, which is actually with the adjacent one, that is this minus J10 so we have taken, and a lot of mutual inductance, and here is in opposite, that means dots are in opposites. One is entering position and another one is leaving position, so it will be minus. So here the mutual inductance value is written as minus J2 I2 equals to 10. So that is our first equation. In a similar way, we will write the second equation, this one, and using Cramer's rule, we have solved this problem and we have got this value of I1 and I2. You can take any other method for solving equations and you just try the methods for practice purpose, because for examination we need to practice. Otherwise, directly examination hall, it is not possible to solve any numerical problems. So I1 minus I2 equals to this one, and voltage across the capacitor is because this is the value of the XC and into I1 minus I2 current here. So I into R, we are getting the voltage drop, and that is we have calculated. In that way, we can calculate this problem. Next problem, find V2 in the circuit given in the figure such that I1 equals to 0. We have to find the value of V2 when I1 equals to 0. Okay. Simple. Now we have applied KVL in these two meshes, and we are getting that 2 plus J4 I1 plus J2 I2, because here mutual induction is the dot conjunction. As per dot conjunction, both are in entering position, so it is plus, here, so it is J2 I2 equals to V1, that is the value. Actually the value of V1 is given, that is equals to 5. The value of V1 is 5. It is the problem. So it is something here. Now, from here, we will form the second KVL equation in the loop 2, and it will be, this will be 2 plus 2 J2 I1 plus 1 plus J3 into I2. Here J2 I1 means it is the mutual induction, this value. Again it is positive, and we know that mutual induction is always something for the another branch current, so it is J2 I1. And 1 plus J3 into I2. So here this value of the resistance should be 1 ohm. Written wrongly 2 ohm, it is 1 ohm. So it will be 1 plus J3 by 2 equals to V2. So now solving this equation using Cramer's rule, we can find out the value of I1. Now as per the question, the value of I1 equals to 0. At that condition, we have to find the value of V2. So putting the I1 equals to 0, we are getting the value of V2 is like this. So ultimately we are getting the value of this 7.9 angle 18.43 degree. Here, while we have calculated I1, but otherwise if we calculate I2, there is no meaning. Because as per the problem, our condition is I1 should be 0. So definitely we need to calculate the value of I1 first. After that, we will put 0 in place of I1, and we have to calculate the value of V2. So in that way, we have calculated the value of V2 by putting the condition I1 equals to 0. Next problem. In the circuit shown in the figure, calculate the current I2 for which I1 will be 0. And also calculate the value of V2 for this condition. Assume x1 equals to x2 equals to 15 ohm and xn equals to 100. So the value of x1 and x2 is given and also the value of xn is given. That means these two values are given and also the value of mutual inductance that is also given. So with help of that, similar way we have formed the Taylor equation for loop 1 and also for loop 2. But here the direction of currents are opposite. So taking consideration, you have formed the Taylor equations. Now again using Cramer's rule, we are getting the value of I1. Now see, we last for like previous problem, here the same condition also given, that is when the value of I1 equals to 0, then calculate the current type. So in place of I1 we have to put 0 and we are getting that the value of V2 is this one. Okay. Now from the value of V2 we will calculate the value of I2. We have just put the value of V2 here and with help of that, we will calculate the current I. So this is the value of current which we are getting at 4.3 angle 153. So problems are simple, but you just need to understand that what is the mutual coupling and where the dot condition are actually true. So it will be plus or minus. That is the main concept here for solving the problems. And other concepts, just like alien equations, are required to solve this kind of problem related to mutual coupling. Next problem. Find the conductivity of the equivalent circuit for the network shown in the figure. So here the dots are in opposite direction. So it will be minus. But for solving this problem, we have converted the linear transformer form into T equivalent, and we know that in T equivalent we have three formation of inductance, that is LA, LB and LC, and the value of LA will be L1 plus M, LB will be L plus M and LC is minus M. So from the direct calculation value which we have already discussed in my last lecture, so from there we have directly calculated the values of this inductance LA, LB and LC which will form the equivalence to circuit. So in place of this mutual induction part, we have formed this one into equivalence form and we have just put it here. So now we have simplified this circuit, and the simplifying the conductivity equivalent circuit, we are getting that V, which is 4 ohm, and we have some of these two inductances, that is J1 and J6 and minus J3. So from there we are getting that J4 ohm. So calculating these three values are directly written J4. Similarly, we have also calculated this one. This is J4, this is 2 ohm, and this is 2 ohm, and this is J4. We have directly just put this plus. So this is the equivalence conductivity for this circuit, and here if we apply KVL, then we find the value. But here that is not possible because value of V is not given. So here you have to just need to form the equivalence form of the linear transformer circuit. So we have just easily formed that one, and this kind of similar problems have generally comes for your examination. So up to this much for today, and this is the last lecture for mutual coupled circuit. Hope you have understood the chapters of mutual coupled circuit. And you just go to the problems. Many problems has been discussed in the book of supplementary of circuit theory, and that will be very effective for your study purpose. So I will prefer that you just go through those chapters and solve the numerical problems by your own hands, and that will be effective for your understanding purpose. Thank you all for listening to the lecture.